So maybe some of you will start loving this course after today's lecture. Why? Because today's lecture, we will deal with you as engineer, materials engineer, okay? What we will do, we will use the knowledge that we got from the previous two lectures, right, to design a material that can demonstrate higher strength compared to others. If you remember, the title of the chapter is Dislocations and Strengthening Mechanisms. So this chapter can be divided into 4 parts. The first part, we talked about characteristics about the dislocations. What are the associated strain field, compressive, tensile? Okay. The second part about how you can make the dislocation slip inside the material. So we talked about different slip systems, which is the combination of slip plane and slip directions. And also we talked about the needed stress that would allow the dislocation move. Because the movement of dislocation will initiate the plastic deformation. So what are the needed stresses or critical resolved shear stress that will allow the dislocation to move? The third part is going to talk about how we can use these two information that we got from the previous lectures to design a material that can demonstrate higher strength. And then the second part will be about how can you increase the ductility of the material. Good? Because as engineer, we always gonna find this issue. If you want to increase the strength of a material, you will lose the ductility. So in many applications, you want to design a material that can demonstrate high strength, yet it has some ductility. So in today's lecture, we will try to talk about mechanisms that can help in increasing the strength of the material. And I need your help, okay, to tell me how can we make the material stronger? And to guide you and to give you some tip, all different mechanisms aiming for the same thing, which is placing or restricting the dislocation motion inside the material. Because remember, dislocation, a plastic deformation will be initiated if there is large movement of dislocations. If you prevent the movement of dislocations, then plastic deformation will not happen, or it needs higher stresses in order to exist. So now the goal is we want to restrict the dislocation motion. Okay, we want to restrict the dislocation motion. What are possible mechanisms that can restrict the dislocation motion?
Maybe cold treatment, doctor?
What?
Cold treatment.
Cold treatment. What do you mean by cold treatment?
Compressing the material at low temperatures.
Okay, that will make the material
denser.
Denser, okay. Compressing.
Maybe it will prevent certain dislocations or not.
Okay, so the first one, as Muhammad said, is called cold working, or also it's called strain hardening. If you remember in the previous chapter, we spent more time on one of the figure, if you remember it. The last figure in that chapter. We say that if you plastically deform a material and then you release the load and then you apply the load again, right? Every time you're gonna find the material becomes stronger, it needs higher yields, higher stresses in order to be plastically deformed, right? Why? Because every time you plastically deform the material, you are increasing the density of dislocation. And also, you are activating more slip planes on which the dislocation can move. So more dislocation will be activated to move. And this will result in more possible interaction between dislocations. And we learned before that the two possible scenarios of the dislocation interaction. One of them is the repulsion if they have the same sign. So this is gonna go in this direction and this is gonna go to this direction. So every time you increase the density of the dislocation, you are increasing the chances of repulsion that can exist between dislocation. And as a result of that, you need higher stresses in order to let the dislocation move in one direction. So this is why every time you plastically deform the material and then you leave the load and you apply the load again, you're gonna find that you need higher strength. Every time you need higher stress in order to plastically deform the material. This is called strain hardening or cold working. It's called cold working. It's called, well, it's not at minus 12 or minus 20 Celsius. It's in room temperature, but that temperature is relatively very low compared to the melting temperature. This is why it's called cold working. This can be quantified by using the following equation, okay, which is equal to the A initial minus A final over A initial all times 100. Okay? So the more cold working you do to the material, more plastic deformation you do to the material, the stronger the material becomes. Okay? If you think you got this point, I would like you to answer this question. If this is the stress strain curve, and let's pick this color, this is curve A, and this is B, and this is C. What do you notice? What is the difference between these three different lines? Which one you think is more stronger? The red, or the green, or the blue? Which one is more stronger?
The blue.
The blue one, but it will fracture faster.
Right, wonderful. So remember, if you increase the strength, you're losing the
Ductility.
the ductility. So it's a challenging task. Yeah. It's not easy for an engineer to design a material that can have high strength, at the same time want to gain some ductility, because you don't want to have a brittle material that can quickly break, right? Okay. Can you imagine that these three different curves for the same material, all of them can be for aluminum, for example. But this different behavior because this material, green, for example, it went through, let's say, 20% cold working. Yani, we have done some plastic deformation. And this one, let's say, 35% cold working. So what is the result of cold working? Is you are increasing the strength of the material, but at the same time, you're losing the ductility of the material. Then one possible mechanism is to increase the to do cold working or strain hardening. Second mechanism. What do you think could be second mechanism?
Maybe we can change the grain size.
Change the grain size. Why do you think changing the grain size can help?
Having small grains results in harder materials because of different slip systems.
Slip systems. Okay. So Abdullah Qasim is suggesting another mechanism to make the material stronger, and he called it grain size reduction. Okay. So if you compare material A with material B, okay, in material A, you got larger grain size, and you want to compare this with material B that has smaller grain size. Why do you think material B is stronger than material A?
Because it has more grain boundaries.
Okay, more grain boundaries.
Higher energy.
Grain boundary, and that will?
Grain boundaries have higher energy.
Okay.
Than the grain.
Okay. What
So
other answer? Yeah, go ahead, please continue. Yes, sorry for cutting you. You can go ahead. So?
Yes, so it's stronger.
So grain energy is higher because the atoms are not organized as inside the grain, right? You have some discontinuity of the ordering of the atoms at the grain boundary. That's good. Okay. So I will use that information. I will build on this information. But do you have another answers? Do you have any other answers?
The grain boundary works as obstacles. That doesn't let the shear stress move into from grain to other grain.
Okay, good. So if you have a dislocation, let's say a dislocation that is sliding on this grain. Now, when you apply it tensile load, that load will be resolved in shear stress, right? And that shear stress will be with different values, right? Remember, we said shear stress equals to sigma cosine phi cosine lambda, right? So the applied stress will result in some shear stress, depends on the orientation of that plane. Okay, great. So some planes in this grain will be activated first. That means the dislocation can move first, while the others, nothing can happen to them. The dislocation will not slip on that plane because the resolved shear stress did not reach to the critical resolved shear stress. Because we learned from the previous lecture, dislocation will slip system will be active only if the resolved shear stress reach to the critical resolved shear stress. Good. So let's assume this plane is active now as a result of the applied stress, because the applied stress results in result shear stress. The result shear stress equals to the critical result shear stress, while the others are not active. Okay, good. Now this dislocation is moving, slipping on this plane and this direction. So all the needed force, or all the needed stress is just to move, to slip this dislocation on the plane. But once this dislocation, okay, intersect with the grain boundary, as Muhammad al-Sa'd said, in the grain boundary you have discontinuity of ordering for the atom. So the dislocation needs more energy now in order to move or to cross the boundary of that grain boundary, or to cross the grain boundary, right? It needs more energy. It wasn't easy as before when it was sliding on this plane. So we need now had additional energy in order to let the dislocation move. In single crystalline material, we don't worry about this. Why? Because we don't have grain boundaries. All what we care about single crystalline material is the orientation of the plane. If this gets activated first, then the dislocation will slip on this plane. And that's it. So the dislocation moves from one point to other, and here you can see step on the surface of the material. But for polycrystalline material, dislocations, if it gets activated, the slip system on one grain, nothing gonna happen to the polycrystalline material until the other grains also get activated. And you can see there are different crystallographic orientation between the grains. So some of them will start some of them will be activated first, while the others still need more stresses. So you see that how the polycrystalline is more restricted when we talk about polycrystalline material. So the formation is more restricted compared to single crystalline material. This is why polycrystalline material are more stronger compared to single crystalline material. Okay, good. So then what's going to happen if the dislocation cross the grain boundary? Now, this grain over here, it has different planes, right? The plane that might be activated first could be, for example, could be, with different orientation. Let's say something like this, right? So now you need additional energy to cross the boundary. You need additional energy in order to change the direction of the dislocation to slip on that plane. Okay? This is why if you place more grain boundary in the front of the dislocation, you will have more restriction for the dislocation movement inside the material. And as the result of that, material becomes stronger. Sometimes it's really very difficult to let the dislocation move from one grain to another. So that will result in piling up dislocation. So the dislocation will pile up. They cannot move, they cannot go to the other grain. So they will pile up on this grain because this grain still me do something like this. Okay. So those dislocations are gonna pile up on the boundary. They cannot go to the other grain because the other grain is still not active. There's no a single plane or single system of this plane is active. That piling up will result in stress concentration that might multiply dislocations in neighbor grains. The main message here is, if you have more grain boundaries, you have more restriction and you're making the material stronger. So this is the second, it's called grain size reduction. Even we can correlate between sigma y, the yield strength, and the size of the grain, D. My question to you, do you think if we decrease the grain size, what's gonna happen to the yield strength? Do you think the yield strength become larger or smaller? Think for a while, just to give more time to others to think also. So let me repeat the question again. If you decrease the size, so you decrease the size of the grain, so you have more grains, you have now more grains, right? Do you think the sigma y will increase or decrease? Think about it, okay? Good. Now I want you to tell me increase, decrease, or it doesn't matter. I want you just to open the mic, unmute yourself, and just tell me increase or decrease or doesn't matter. Okay, just randomly open the mic.
Increase.
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 Doesn't matter.
Increase.
Okay, we have 32 people in this room. I only heard 8 people.
Increase.
وانا
Increase.
كنت بقول
Increase
انكريز يوم قلت doesn't matter بدأت اشك في الموضوع.
Okay, just say increase, decrease, doesn't matter. If you think it doesn't matter, just say it doesn't matter.
Decrease.
Increase.
Increase.
We have 32 people in this room.
doesn't matter.
Okay. Okay, good. So for those who say it doesn't matter, okay, can you tell me why the others said increase? Try to think. So that's actually. For those who said it doesn't matter, why we got a good number of people who said, no, yes, it matters and it will increase.
لأن الستريس يا دكتور هي الفورس على الاريا، بس هل الاريا لها دخل في الجرين سايز؟
Here we are talking about the yield strength of the material. Yield strength of the material is it's yield strength at which the plastic deformation will start, at which the dislocations will slip. ها ما في حد جاوب افا طيب طيب اللي قالوا انها it doesn't matter, can you tell me why you said it doesn't matter?
I said that because I think the grain boundaries affect on the plastic deformation after the yield strength, not before. So just
For those who said it will increase, why do you think it's going to increase?
It's harder to start the plastic deformation.
Okay, because sigma y means starting or initiating plastic deformation. To initiate plastic deformation, you have to move the dislocation. If you decrease the grain size, that means you are increasing the grain boundary. If you're increasing the grain boundary, it's going to be harder to move the dislocation, right? So if you decrease the grain size, you have more finer grains. That means you will make more restriction of the dislocation to move. If the more restriction of the dislocation to move, then it will be difficult to plastically deform the material. That means sigma y will be higher. Okay?
Doctor,
Yes.
ذكرت أولا dislocations will stack until they will form another on the other grain.
No, I'm saying in polycrystalline material, sometimes the neighbor grains might not be activated. So ايش اللي حيصير؟ In addition to the applied stress that you're applying from outside, there will piling up of dislocation that will place another, it's called stress concentration on this to initiate the dislocation or to result in or to produce some dislocation in other grains. So when I talk about this, I just want to mention that polycrystalline material, it's more stronger because the plastic deformation would not be only the result of one grain if it gets activated. It's the result of, the what's happening to the whole grains, to all grains.
Okay, now I get it.
طيب. Good, wonderful. So this is the second case. The third case, okay, so the third case is do you think if you have compressive field, tensile field, do you think the material is happy about what's happening here? Do you think the material is happy about what's happening here? Do you think the material is happy about having dislocation or not?
No.
No. Why? Because there is additional energy, right?
Yes, because you want like يعوض الانرجي اللي
So, right. So when you have a dislocation, there is an energy that associated with this energy that will increase the energy of the system. صح ولا لا؟ وبالتالي the third mechanism is called solid solution strengthening. We will try to find ways to cancel those strain around the dislocation. One way to do that is by placing larger atoms here or smaller atoms. So larger atoms will push the atoms away. That will result in compressive strain field. And the smaller one will pull the atoms toward it. That's going to result in tensile strain, right? So we're going to use this to play with the compressive and tensile strain around the dislocation in order to minimize the energy. Do you think if you minimize the energy, the material becomes stronger or weaker?
Stronger.
Stronger because if you minimize the energy of the system, the material becomes stronger because it becomes more stable, right? And it will be difficult to take the material from the stable state, right? So this is why what we can do, we can add these two ideas, these two things here. So what we can do, we can place smaller atoms in top of the dislocation line that will result in tensile. And we know in top of the dislocation what we have? We have compressive field, right? And below the dislocation, we can place larger particle, right? And this larger particle will result in compressive, right? In compressive, and we know that under the dislocation, actually we have tensile. So this and this, so this compressive might cancel the tensile, and the tensile also can cancel the compressive. So we are lowering the energy of the material. It's called solid solution strengthening. So we are pinning the dislocation in its position. We are preventing this. Now the dislocation not only need force to break bonds, but also it needs to get outside of these two obstacles that you see here. Okay? So this is the third mechanism that we have in order to make the material stronger. So the first one is called cold working. The second one is called grain size reduction. And the third one is called solid solution strengthening. Okay, let's go to the book and let's try to see some figures and equations that are related to these three different mechanisms. Okay, let's see, where is the book? It should be here. So desktop. So what do you see right now? What do you see?
Materials research slide.
صف المكتب.
Okay, good. Okay, good. Do you see me now?
Yeah, now the book.
Let me just use it because I realized that when I maximize it, my video does not appear in the recorded video. Okay. Okay. Good. Now, remember, the title of the chapter is Dislocations and Strengthening Mechanisms. Right? Good. Okay. Great. So the first one here, it's called the grain size reduction. So strengthening by grain size reduction. So this is a quick revision, okay? Grain size reduction. What's going to happen now? The dislocation need to cross the boundary and to change direction in order to slip to continue in order to continue slipping. And we said that if you reduce the grain size, okay, the sigma y will increase. So this is the grain size diameter. If you increase the grain size, so increasing grain size is going to go from right to left. If you increase the grain size, the yield strength will decrease. So if you increase the yield, the diameter, if you increase the diameter, the yield strength will decrease. Similarly, if you decrease the diameter from left to right, you're going to increase the yield strength. This equation is called Hall-Pitch equation, where it's correlating sigma y with the grain size diameter. This only applicable, so this is not applicable to very, 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 very fine grains, very small grains, and also not applicable for large, very coarse grain, okay? But for most of the material, the average grain size, beyond this limit, this equation is valid, can be used. Okay, good. The second one is, the second mechanism, it's called solid solution strengthening. So we can place larger atom or smaller atom in order to cancel some of the strain field that is associated with the dislocation. So smaller atom will result in tensile, larger atom will result in compressive, and by placing this on top of the dislocation or this below the dislocation, that will cancel the strain that's associated with the dislocation. Notice here the tensile strength of the material, the yield strength of the material will increase as the result of, in the solid solution, if you are adding nickel to copper. If you add more nickel, what's going to happen? Up to 50%, the tensile strength will increase because you have more restriction for the dislocation to move. Now, this is solid solution. Huh? Remember, you have a host, right? I have a solute and you have solvent, right? So if you add more solute in the solid solution, okay, you're increasing the yield strength and tensile strength. But at the same time, as we mentioned at the beginning of this class, if you get more strength, you're gonna lose the ductility, elongation. Okay, here expressed in terms of the elongation. Good. The third mechanism is called strain hardening, and also it's called cold working. Okay, cold working of a material will increase the yield strength of the material. As you can see here, let me zoom in more. Okay, the yield strength of the material and also the tensile strength of the material will increase for different material, right? As a result of how much cold working you did to the material. Similarly to the yield to the tensile strength. So if you do more cold working, you can increase the tensile strength and the yield strength. This is very important topic. Very important topic. Can you imagine a material, for example, let's say, okay, a steel. Let's deal with a steel. Okay, imagine you have a steel that you have done only, let's say, 5% cold working. That will take the material from, let's say, the 650. So at zero cold working, how much you got the yield strength of the steel? Is around 450, right? So it's around 450. Okay, it's around 450. So you took it from here, you can increase the yield strength from 450 all the way to 650 megapascal. Such improvement in the strength, it's only the result of the cold working. Okay, good. But in the same time, as we mentioned, if you do cold working, you are losing the ductility of the material. See, the ductility is decreasing, right? So the ductility. So you're gonna sacrifice some ductility of the material. Good. If we want to compare the same material stress strain curve, but a different cold working, you can see clearly that all the, there's a big difference in the stress strain behavior of the material. You can see that how the material zero cold working behave, and if you do only 4 weight %, how it can increase the tensile strength of the material and also the yield strength of the material. If you do 24%, completely different behavior that you can see from the material. The message today, we can play with the property of the material, with the behavior of the material, if we can change the structure. And today, we talk about different mechanisms that can play with the structure of the material that will allow the material to gain more strength. The goal that we have is how, or whatever mechanism we are coming up with, the goal is we want to restrict the dislocation motion. So I will stop here. I will see if you have any